The Beecroft Building is extremely well designed to achieve and maintain a position at the frontier of physics research.
The attention to detail is really phenomenal, but what the scientists then do is just exquisite.
Having been involved in the technical design of the labs has helped us get to a point where we're able to do the research better here because we've got facilities that are built to support specific research.
I always thought that it wouldn't make any difference coming to a different building, and I was completely wrong. This place is wonderful.
My name is Pierre Van Ziel. I'm the Facilities Manager at Physics, and we're standing outside the Beecroft Building. It's a building of two halves, offices above ground, and below ground, state-of-the-art labs. Come along. We're in the bottom of the Beecroft now. In normal operating, this will be a dead space, totally quiet, vibration-free. The building is a very rigid structure. I'm standing on 1¼ meters of concrete. Now that's still not going to be rigid enough for the science, so we have our friends the keel slabs.
Now this is a 30-ton inertial mass of concrete, and it is suspended on an air spring. So the whole system acts a little bit like the suspension on your car, but this is the most plush suspension you can imagine. This technology is not designed to remove vibration of the whole building. It's designed to take any vibration that is in the building and stop it being transmitted into the laboratory, and the floor of the laboratory sits on top of this keel slab.
Why do we need such a low vibration and low temperature environment? My research is focused on exploring quantum mechanical phenomena. We're taught to believe that they're hidden from us at the atomic scale, but I have never believed that that's true. You could, in principle, develop a microscope which, if it had the correct environment and quantum mechanical capabilities, should be able to visualize those quantum waves. They assumed that there's no way to make a laboratory in which you can make mechanical objects which can be moved around, but then made stationary with vibrations with relative distance changes smaller than the diameter of a nucleus. I didn't assume that it was impossible and figured out the specifications for a laboratory.
Welcome to the laboratory on level B2, and this is the lab directly above the keel slab area that we visited previously on B3. So the researchers take the same ideas as we have downstairs, and they have this large rigid metal frame that's filled with tons of sand, and then we have an air spring, and suspended on top of that air spring is this tabletop which is filled with a ton of lead shot. Exactly the same principle. We have a lot of mass, we have a flexible link, and then we have another large amount of mass, and that prevents us transmitting vibration from the keel slab into the experiment. It's one of the most still environments on the planet.
The Beecroft Building is a third-generation version of this ultra-low vibration technology, and at present, as far as we can tell, it is the best laboratory of this type in the world.
I just find that really fascinating. You can write down an equation, a load of squiggles on a piece of paper, and it can help you understand what's happening in the real world. But having done that, we then have to get our experimentalist colleagues to test these ideas, and therefore we need to be close to them.
I don't know if this is the same for all scientists, but when you get to show people what you're really excited about doing, it's just great. For me, the building is unique because we have labs which are designed from the ground up for the research that we're doing. You can't hear our lab yet, although when we open this door you'll start to hear it a little bit. Inside here is where we have these dilution refrigerators which are cooling down to 1/100th of a degree above absolute zero, superconducting quantum computing experiments, and they're all actually running right now, so there are prototype quantum computers running here in the fridges.
A quantum computer is a machine that can process information, making full use of the laws of physics. You might think that a normal computer already does that, but actually it doesn't. They're not using a key piece of physics which actually can greatly enhance how you can process information, and that's quantum mechanics.
Given the scenario we're in at the moment, there's very likely a virtual student sitting here right now in another lab doing an experiment, running the equipment here.
That doesn't necessarily help us to interpret quantum mechanics. It's tricky for humans to understand what's going on. It's very counterintuitive. We just take quantum mechanics and all its counterintuitive content and use it for something useful, which is computing. It will, once fully realised, completely change the world.
We wanted somewhere which would promote lots of discussions, lots of random people meeting with each other in corridors and then going off to talk about physics.
We're here in the Rudolf Peierls Centre for Theoretical Physics on the first floor of the Beecroft. It's a lovely breakout space. You can hear other conversations going on. You could listen in and think, oh, I should go join in that. The theoretical folk amongst us like to either be brainstorming or quietly thinking.
Here there are lots and lots of theoretical physicists doing different sorts of physics. We're looking at something which is called active matter. Our body is an engine. We move around, but our cells move around as well. And I'm trying to understand from a physics point of view how that works. A troop of starlings in the sky will fly around in very beautiful patterns. But what makes that pattern? Is it just physics, or is there some biology in there as well? And if you look at cells, again, those make beautiful patterns as they move around on a petri dish or in the body. And those patterns are important for the way cells and tissues develop. And we're trying to understand how much of it is physics and how much of it is biology.
I have worked at half a dozen of the world's leading physics institutions, and I must say that the intellectual excitement, precision, quality of thought going on in that environment is really wonderful.
We attract super young people. I'm looking forward to a future where we continue to have these very strong collaborations with scientists from Europe and from the rest of the world. And having them all work together is something I feel is very, very important, both for the science and for international relations.
It's very stimulating, it's very encouraging. It really drives things forward as a cultural element of how physics at Oxford works.
We can do theoretical physics anywhere, but we can do it better here.